let's start with section 1.1. That's about the nucleus. So this will be review from any other chemistry class that you've taken before, but it's still important that we have this down. I have some structures here. The nucleus, right? That's, of course, the dense center of an atom. And when I say dense, I don't mean just kind of dense. I mean really, really dense. I mean almost all of the mass of the atom is contained within this tiny, tiny structure in the very center of it, right? So the nucleus, it contains protons and electrons. So protons are positively charged particles. Neutrons have no charge. And protons and neutrons are approximately the same size. So that nucleus, if we were able to see it, it would sort of look like a bunch of grapes where we've got these little protons and neutrons that are clumped all together in the center of it, right? So electrons are outside of the nucleus. Electrons, of course, have negative charge, and they're nearly massless. What does that mean? That's talking in relative terms, comparing to protons and neutrons. So if we were to set our scale on the mass of a proton or a neutron, which is the atomic mass unit, by the way, electrons would have a tiny, tiny, tiny mass, almost immeasurably small. So let's look at the diameters here. The diameter of an atom, about 2 angstroms. So an angstrom is a pretty convenient unit that's used when talking about sizes of atoms and subatomic particles and things like that. So the angstrom itself is 10 to the minus 10 meters. So 1 power of 10 smaller than a nanometer. There are, in fact, 10 angstroms in a nanometer. So let's just write that over here so we know that 10 to the minus 10 meters. So 2 angstroms across. Take a look at this. If we're talking 10 to the minus 10 meters for the atom, the nucleus is on the scale of 10 to the minus 15. So 5 powers of 10 smaller in diameter. So what's 5 powers of 10? 10, 100, 1,000, 10,000, 100,000. So the nucleus is 100,000 times smaller than an atom. So if I had a nucleus that was 1 meter across, just if we were to change it up a little bit, if I imagined a huge atom with a nucleus that was 1 meter, like a beach ball, the whole atom would be 100,000 meters. So it gives you an idea of how tiny that nucleus is, and especially when you consider almost all of the mass of the atom is contained within that tiny little nucleus. So a couple of terms we use to classify atoms. Atomic number, which is abbreviated Z. Atomic number is just the number of protons. And that determines which element an atom is. So atomic number is listed on the periodic table. So carbon has an atomic number of 6, which means it has 6 protons in its nucleus. And every carbon atom will have exactly 6 protons. That's what makes it carbon. So mass number has sort of weird abbreviations. Mass number is A, but mass number is the number of protons plus neutrons. So it's the number of massive particles in the atom. Remember, protons and neutrons have about the same mass. No other subatomic particle comes even close. Electrons are essentially massless compared to those. So if we count up how many protons and neutrons there are in an atom, that's its mass number. So isotopes are defined as having the same number of protons, call those P+, and different number of neutrons. So if I have 2 or 3 or 4 atoms, they all have the same number of protons. That means they're the same element, That's important. I cannot have two isotopes that are carbon and boron, for instance. Right? In order for two things to be isotopes of each other, they have to both be carbon. But since neutrons are uncharged, we can vary the number of neutrons without really affecting too much. I mean, it changes the mass of the atom. That means we have the same atomic number. So I was going to write An, but let's use the actual symbol. Let's write Z for atomic number with different mass number, different A. So atomic number, remember we said, will define an element. Mass number will give us an idea of the mass of that particular isotope just by counting subatomic particles. So atomic mass, please don't confuse that with mass number. Atomic mass is an actual measurement measured with the mass spectrometer. It's the weighted average mass in atomic mass units, that's AMU, of any element's naturally occurring isotopes. So for carbon, its atomic mass is 12.01 AMU because carbon contains mostly carbon-12 with 6 protons and 6 neutrons. Right? The vast majority, over 99%. Okay? There's also carbon-13, 6 protons, 7 neutrons, and carbon-14. 6 protons, 8 neutrons. Carbon-12 has a mass of 12 AMU, but the atomic mass, when we weight the average of it, because we have a small amount of these heavier isotopes, the actual weighted average creeps up a little bit above 12. So that 12.01 is going to be an important number. We don't do too many calculations in this course, but we'll keep that in mind.